All right, welcome everyone to the November general meeting of the Kalamazoo Astronomical Society. And of course, welcome to the first installment of the Eclipse series. So starting tonight for the next 5 months at general meetings and astrophotography SIG meetings, we're going to have a full series of very special speakers and workshops. And so we still have people filing in here at the Kalamazoo Area Math and Science Center. Our doorman, the venerable Mike Sinclair, I believe, is still downstairs. So we're going to give you a quick introduction to the Eclipse series here. If you haven't looked at the website or haven't really seen much of the flyer, maybe you just saw this during our immense publicity campaign. Maybe you saw the MLive article or something like that and came in and joined us, and you don't know anything about the rest of the Eclipse series. So let me share the screen here for you, and I'm on the wrong page, which is fine. So I'll show you how to get there. So of course, from our home page, which is here, you just go to the activities menu where all of our activities are. You can see we have the Eclipse series here. And of course, the purpose, as you can read here, the purpose of the Eclipse series is just to build excitement. Like I was telling members at our meeting last month, pardon my French, but I am as excited as hell for the next total solar eclipse next year. For the 2017 eclipse, I was waiting for that since 1983. I haven't been waiting for this one as quite as long, but now that I've seen one in 2017, I cannot wait to see another one. And so a big reason why I went through a ton of work to put this together is I want to share my excitement with everyone. And the best way I can think of doing that is doing these special presentations during our regularly scheduled activities. So as I mentioned, we're going to have all kinds of speakers. Of course, I'll introduce our tonight's speaker here shortly. So we'll kind of go past that one because that's where we're at tonight. And so starting November 17th, we have Alan Dyer. He'll be giving a 2-part presentation. If you just have a smartphone or a DSLR or a mirrorless camera, and you want to try to take pictures of the eclipse, either really simple or really complicated, this is the presentation for you. So Alan Dyer, he wrote a book on this, and he'll be giving us as much information from the book as he can. But of course, the big point of this is, besides the wonderful presentation, if you need to ask someone questions live, because you can't do that on a YouTube video, you can join us for our first installment here of his 2-part lecture on November 17th of how to photograph the eclipse. And again, it could be simple stuff or really complicated stuff. Still shots, time lapses, all that stuff. And of course, once you get all those pictures, you're going to want to know how to process them. And so that's what Alan Dyer will talk about during our December installment in the series on December 15th, how to process your pictures. And then we ring in the new year with another installment right here at the Kalamazoo Area Math and Science Center and also on Zoom. Very famous eclipse chaser and meteorologist Jay Anderson will be joining us here live, assuming the weather between here and Canada isn't bad. But he's still planning on joining us here in person. So that's where we definitely want a huge crowd here to meet him and greet him. And of course, if you have any of his books, he'll be happy to sign those. And so Jay will be giving the presentation, Moonshadow Madness and Eclipse Journeys. And I definitely have some of that madness for the eclipse. And back for the astrophotography stuff, if you do have a DSLR camera, maybe a mirrorless, depending on the program, and you don't want to use your program during the eclipse, you want to watch the eclipse and not your camera, these guys, Fred and Xavier, they will show you how to use software they created, how to automate your eclipse imaging. And so Fred will be talking about Eclipse Orchestrator, which I just used again for the annular eclipse earlier last month. On October 14th, it worked like a dream again, just like it did in 2017. But Eclipse Orchestrator is only for the PC people. So if you're a Mac person, that's where Xavier comes in. He created Solar Eclipse Maestro, and that's for controlling your Mac-based computer. So we got both bases covered. If you're a Linux user, I guess you're just out of luck. I'm sorry. If you've ever been to the website greatamericaneclipse.com and saw this guy's wonderful maps, he'll be here basically showing, the eclipse path with his maps that he created, and giving all kinds of interesting tidbits, things you can discover all along the path of totality. So Michael Zeller will also be here in person in Kalamazoo, and that'll be February 2nd. And he'll be speaking specifically about the April 8th total solar eclipse. And then, of course, we have Mr. Eclipse himself, Fred Espenak, probably one of the more famous people related to eclipses in the world. He'll be coming to us via Zoom. We were hoping to have him here in person, but he is so focused on not missing the eclipse, he didn't want to take a chance of traveling and getting COVID, during his trip and not being able to go see the eclipse. So he's also going to join us on Zoom. And so again, if you want to see one of the most foremost eclipse experts in the world, you can join us here at CAMSI or on Zoom for that. And kind of a bonus, if you've only seen our flyer, you might not have seen this yet, but Alan Friedman, he lives in Buffalo, New York, and they have about as lousy of weather as we do, but somehow he takes the most incredible solar images you will ever see. And so this is more centered on imaging just the sun itself, but you can image the sun, while the eclipse is going on, and he can show you how to, make those images really, really sharp. So Alan Friedman is going to close out the series on March 15th. And I'll just mention while I'm here, the other half of the eclipse series is me going to 30 different libraries and schools throughout Southwest Michigan. And again, this was a lot of effort to put together, both the speakers here for the club and me going out in the community. And of course, it cost a bit of money to put that together. And we want to thank the Irving S. Gilmore Foundation for funding the entire Eclipse series. And so to them, we are very grateful. So if you go to the website here, you can scroll down and see the list of all the places that I'm going to. Most of them are March. So if you expect to contact me in March and get a quick reply, you probably won't, because I'll be on the road so much. But it's going to be a ton of fun. And again, those start up here just next week. I do 3 in November. Then nobody's scheduled December or January. You got the holiday season and all that sort of thing. So after November, we go to February, and then March is pretty book solid, pretty much every day of the week. So that is the Eclipse series. And yes, you're very welcome. And so it does make me very happy to see all of you here tonight. And we currently have 105 people at home on Zoom. So that definitely outdoes the Astronomy Day event that we had Tyler at, that didn't quite go as we had hoped because of a whole variety of reasons. Okay, so I think I killed enough time. If Sinclair isn't up here by now, it's his fault. So we're going to introduce our guest speaker and get going here. So we'll have to lower the lights here shortly as well. We'll just pick a button and go from there. So tonight's special guest speaker first joined us on April 29th, 2017 as part of that year's award-winning Astronomy Day celebration. We did win the best event in our population category for that year. He is a professional astronomer, author, and artist. He earned a BA in physics from Reed College and a PhD in astronomy from Cornell University. He is a former professor of physics and astronomy at the University of Redlands in California, and has worked as an astronomer at both the U.S. Naval Observatory and Lowell Observatory. For over a decade, he has worked with the National Park Service to turn the national parks into the single largest source for public science and astronomy education in the world. And I know they turned the lights out a little earlier than I wanted, but I was going to show 2 of his postcards that I have hanging up in my room. They sit on one of my picture frames. And so here are two of his postcards. One's from
Devil's Tower.
Devil's Tower. I almost had it out there. I've been there twice. It's really, really cool. I can't see where the aliens landed during Close Encounters, though, but they're there. And of course, I picked this up on the road during my 2017 eclipse trip. And so he has a lot more art out there that you can check out at, I'm assuming, tylernordgren.com, right?
Yeah.
And of course, he is the author of this excellent book, Sun, Moon, Earth, The History of Solar Eclipses from Omens of Doom to Einstein and Exoplanets. And also Stars Above, Earth Below, A Guide to Astronomy and the National Parks. So without further ado, please welcome Dr. Tyler Nordgren.
Thank you. All right, I'm going to share my screen here. And let's see. All right, how's that work? Does folks see my screen?
Yes, we can.
Wonderful. Okay, so once again, let me just thank you for inviting me back. I cannot believe it was almost 7 years ago that I was there, but then I can almost hardly believe it was almost 7 years ago that we had the 2017 Great American Solar Eclipse. That event has turned on so many people like yourself to what an amazing, awe-inspiring event a total solar eclipse can be. It had been 38 years prior to that since the last time the United States, the mainland United States, had a total solar eclipse. That half the people that were alive back in 2017 had not been alive the previous time a total solar eclipse had touched the continental US. So that was a groundbreaking moment, and this is surely to be even better this time. So what I'd like to do is start off just to read the first couple pages from my book, Sun, Moon, Earth, that talks about what that experience is like to actually see totality for those people in the audience who haven't had a chance to see one yet. All right, so let me start here. It's not even lunch yet when something takes a bite out of the sun. It's only a tiny notch at first, all but invisible without my cardboard eclipse glasses. Were it not for the shouts from the crowd around me on this August day, I would never have noticed. But now that I'm watching, I can see the bite grow bigger. It's the edge of our unseen moon. The sun is being eclipsed. It takes 40 minutes for the dark notch to grow so big that the sun is now a crescent. But even with most of the sun covered, the heat of the day is still intense. I take off my glasses and take refuge under a tree. There in its shadow, I see 1,000 bright crescents swaying in the grass to the time of the breeze in the treetop. Every one of them is an image of the sun, projected on the ground when each tiny gap in the leaves overhead acts as a camera obscura, a pinhole camera. Nearby, children have spotted them too and begin to yell and giggle as they point and play among the bright little arcs. Had I not known what was happening before, this oddity would certainly have revealed the eclipse in progress above. After an hour has passed, only 20 minutes remain until totality begins. The life-giving nature of the sun is no longer an abstract concept. The sky has grown darker and colors are strangely wrong. The landscape is sapped of saturation. The worlds are aligning. With 10 minutes left, the conditions change quickly. The world has turned to twilight. The shadows of trees sharpen, as if lit by a single spotlight. Instead of coming from a round yellow disk set amidst a bright blue sky, all illumination now comes from a narrow white crescent in a colorless dark vault. I put my glasses back on for these final few moments in the partial phase and can see the remaining crescent shrink as I watch. The crowd rises, conversations hush, and I notice for the first time that all bird song has ceased. The birds have returned to their nests to sleep in the unexpected night. An unseasonably cool wind blows across my arm as the temperature drops. The eclipse becomes a multi-sensory experience of sight, sound, and touch. So little of the sun is left that surely totality should begin at any second, but I can't tear my eyes away to look at my watch. Suddenly, the sun's thin sickle of light breaks apart into an array of brilliant specks that dance and shimmer along the moon's jet black rim. They're called Bailey's beads, the last rays of the vanishing sun streaming through actual mountain valleys along the curved lunar surface. I finally remove my protective glasses to see them quickly wink away until a glorious diamond ring appears, a single glistening star set in a band of white radiance encircling the moon. Then the spot collapses upon itself and is gone. We have reached totality. Where before there was light and heat, now there's only a cold black hole in the sky, surrounded by a ghostly crown, the corona. A ring of immense pearly tendrils envelops the darkness and stretches off in the sky in all directions. It is unimaginably beautiful and only ever visible during these few precious minutes of totality. All around it are the brighter stars and planets, invisible until now. It is a day that has become night at noon, with the sun, moon, planets, and stars overhead all at once. As an astronomer, I know the mechanics of the celestial alignment, yet in this moment of totality, I fully understand the difference between knowledge and feeling. Okay. If ever there was anything that could even shine a partial light on what it must be like to be within the shadow of the moon during totality, this perhaps can give you a tiny inkling of what that might be like. And it's not an unreasonable thing that we feel this fear and this awe at the moment of totality. The first time I got to see a total solar eclipse was in 1999, 20 years after my first chance to see a total solar eclipse, which was when I was a 9-year-old kid in Portland, Oregon, when a total solar eclipse in 1979 went directly over my house. But I was so filled with fear from all the local news media that said, "Don't look at the sky, you'll burn your eyes out," that I thought for sure if I accidentally saw the sun during a total eclipse, some strange rays must come out that would burn my eyes to a crisp and I'd go blind in an instant. So I hid in the house and I watched my very first total solar eclipse on the TV, not even turning around to look out the window lest I went blind. And that kind of fear is something that throughout human history, people have experienced when they've seen a total solar eclipse, because to see the sun suddenly turn black in the middle of the day is the most unnatural of what we now know to be a natural phenomenon. And so when you take a look at, say, Hindu mythology, for instance, there's a wonderful story of Rahu, this giant bodiless head, an immortal head, eating the sun. This comes from India. And if the people down below make enough of a noise, they might startle Rahu. And as he tries to eat the sun, it'll fall from his mouth and the eclipse will just be partial. In Indonesia, there's the exact same story. Instead, it's Kalarau. But it's the same thing, this bodiless head trying to eat the sun or the moon. And this is what gives rise to both solar and lunar eclipses. This connection that we see between solar and lunar, between the sun and the moon, also takes place in other cultures. For instance, in the American West, the Pomo people of Northern California have the story of a bear walking along the Milky Way. And here's a photograph I took in Yosemite showing the Milky Way overhead. So imagine a bear walking along that Milky Way, that starry path in the sky. And as it comes across the sun, the bear fights with the sun. And in fact, the word for eclipse in the Pomo language is actually sun-bit bear. 2 weeks later, the bear continues on and encounters the moon, and again has a fight with the moon. And so again, you see this connection between solar eclipses and lunar eclipses. Well, we now know what causes eclipses. And so in fact, yes, they are connected. Eclipses of both the sun and the moon are the interplay of light and shadow between the sun, the earth, and the moon. During a lunar eclipse, the moon moves into the earth's shadow, and every single person on the night side of the earth gets to see a lunar eclipse. So for instance, here's a photograph that we see of a total lunar eclipse. And this is a photo that I took from Grand Tetons. Yes. And you see the moon moving into the earth's shadow. And as it does, it takes on this orangish glow. The media, as much as I hate it, refers to this as the blood moon. But in fact, that That orangish red color comes from the light of sunlight filtering through the Earth's atmosphere as it illuminates the moon. Because during the moment the moon is in the Earth's shadow, the only illumination on it is light that has filtered through the Earth's atmosphere. And if you think about what it would be like to, say, stand on the moon during a lunar eclipse, you would look up into the sky and you would see the Earth passing between you and the sun. And so, in fact, when we see a lunar eclipse here on the Earth, if there were ever to be astronauts on the moon again, they, in fact, would see a solar eclipse. And at the moment of totality, as the Earth is perfectly aligned with the sun, the only illumination would be this orange ring of light around the Earth, and that's the Earth's atmosphere. And if you think about, well, what is that light? That is the light between the daylit side of the Earth pointing towards the sun and the night side of the Earth pointing towards the moon. It's that moment between day and night. Well, that's sunrise, that's sunset. What you are seeing is the orange glow of every single sunrise and sunset taking place on the Earth simultaneously, shining onto the moon and being reflected back to us. Personally, I find that a far more beautiful idea than blood moon, but that's what the media has found, and so I guess we're stuck with it. Okay, the next visible total lunar eclipse from the US is actually going to be a couple of years off, March 13th and 14th. But, and in fact, here you see the moon having moved through the circular shadow of the Earth. And in fact, that is one of the ways that people first realized that the Earth was a sphere, because no matter where in the sky the eclipse occurred, the Earth's shadow is always a circle. And the one geometric shape that always casts a circular shadow is, of course, a sphere. All right, well, okay, so that happens when the moon goes through the Earth's shadow. 2 weeks later, the moon comes around to the other side, and you have a solar eclipse as the moon passes between the Earth and the sun. So there's our first connection. Solar eclipses and lunar eclipses always happen either 2 weeks before or 2 weeks after one another. And in fact, we just had a solar eclipse back on October 14th. That was an annular eclipse. That happens because the moon's orbit around the Earth isn't perfectly circular. Sometimes it's a little close, sometimes a little far away. In fact, 2 weeks before the October 14th annular eclipse, we had what, again, the media has latched onto as a supermoon, where the full moon happens when it's at its closest point to the Earth, which means if you have a solar eclipse that occurs 2 weeks after a supermoon, it's going to be at its most distant point from the Earth, which in this case means that the moon is just too far away from the Earth to completely block the sun's disk, and you get a ring of fire where the alignment is perfect. So for instance, here's a photo mosaic a friend sent me of what an annular eclipse looks like, and perhaps members of our audience went out to the American Southwest and got to see the October 14th annular eclipse for themselves. This is a photo I took back in 2012 of the previous annular eclipse that had coincidentally also gone through the American Southwest. Here I am out in Pueblo Bonito in Chaco Culture National Historical Park, a 1,000-year-old ancestral Pueblo and great house. And there the annular eclipse occurred right at sunset. And so I got to watch as the eclipse sun set off in the west. And I have to say, it was a truly moving experience. And it just so happened that Chaco was also in the path of the annular eclipse just last month. So if you take a look at what the path of that annular eclipse was, it went through some of the most spectacular landscape out in the American West. Easily a dozen national parks, many more state parks were in that path of the annular eclipse. And as Richard mentioned, one of the things that I also do is I design artwork for national parks to help promote both their dark starry skies, but also solar eclipses and other astronomical events. So here's a poster I designed for Bryce Canyon, as well as one that encompassed all the parks that were along the path of annularity. So what can you learn from an annular eclipse? Well, just as we learned that when you have a lunar eclipse, that circular shadow of the Earth tells you something about the shape of the Earth, the track of an annular eclipse actually tells you something about the moon. And one of the first people to write about this was Anaxagoras, a Greek philosopher back in about 478 BCE. He was a philosopher living in Athens, Greece. And it just so happened that in 478, an annular eclipse passed right over Greece. And Anaxagoras had the idea that perhaps eclipses were the result of this interplay of light and shadow between the sun, the earth, and the moon. So in fact, he was absolutely totally right about this. And that led to a couple really amazing realizations. The first is if a solar eclipse is where the moon is passing between the earth and the sun, then that means that the moon must be closer to us than the sun. All right, that's pretty amazing. Secondly, if the moon and the sun look about the same size on the sky, have about the same angular size, yet the moon is closer to us than the sun, then that means that the sun must be larger than the moon. Again, what another amazing phenomenon to have grasped from just this simple idea that the earth, the moon, and the sun were actual physical bodies shining light upon one another. All right. The last thing that Anaxagoras hypothesized from this is that, okay, so if the solar eclipse is the moon moving between us and the sun, then that shadow that the moon casts onto the earth must tell us something about the size of the moon. The moon has to be at least as big as the shadow that it casts. So he reasoned if he could figure out how big that area was on the surface of the earth where people saw that ring of fire, then he can deduce the moon has to be at least as big as that. Okay, so how do you do this in a time before GPS units? Well, being a person living on the seashore, in fact, the Athens being the great trading center that it was, he realized all he had to do was go down to the port and talk to the captains, talk to the sailors who came into port after this eclipse and ask them, had they actually seen that ring of fire that happened just a few days ago? And depending upon whether they did or didn't, he asked, okay, well, where were you at that time? And based upon who saw it and where they were, he was able to figure out how big the moon's shadow had to have been. And we all know this because several hundred years later, in fact, about 600 years later, Plutarch wrote that Anaxagoras says that the moon is as large as the Peloponnesus, that peninsula of Greece. And in fact, yes, it is at least that large. But think about what a wonderful discovery that was to look at that interplay of light and shadow and be able to draw a conclusion about how big and how far away the heavens must be. That is something that you cannot learn about the universe if it's bodiless heads or dragons or other demons and beasts that are biting and swallowing the sun and moon. This is the origin of science. All right, well, we had an annular eclipse back on the 14th. And in fact, 2 weeks after that, if you were in Europe, there was a partial lunar eclipse. So there's that connection between solar and lunar eclipses. But an annular eclipse is not what brings us all here tonight. What we're going to be talking about is that other kind of solar eclipse, the one where the moon is a little closer to the Earth at the time that it passes directly between us. And so the moon does completely block out the light of the sun, and the eclipse is total. And that's what's happening on April 8th of next year. So you get that partial eclipse, and then instead of a ring of fire, you get that last final moment when the last tiny bit of the sun disappears behind the shadow of the moon. You get that diamond ring, and then you get the total solar eclipse. And for those who have seen them, it is a sight that you will never forget. All right, so let's talk a little bit about what these eclipses have been able to tell us from a scientific sense. All right. So the 1800s, were a pretty big time. They were the origin of the scientific expedition. You had the ability to predict, thanks to Newton's laws, and the work of Edmund Halley, exactly where total solar eclipses were going to occur. And so you had expeditions that would travel to these locations specifically to look at these events and to understand what you could about the sun and the moon. All right, so what we see here are two drawings made of different solar eclipses from the 1800s. The one on the left is from 1842. This is one that Bailey himself made from Italy, northern Italy. The one on the right is from 1858. And so the first thing to notice there is, ooh, this corona. In fact, Bailey was the one that coined that term, corona, for crown. Looks different between the two. Okay, so there's interesting thing number one. Interesting number two is in Bailey's drawing, he's got these red splotches on the limb of the moon. Okay, that's interesting too. What are these? There's the first question. All right, for a while, there was some uncertainty as to what that corona and what those red protuberances, we'll call them prominences, what they were. Were they phenomena having to do with the sun, or were they phenomena having to do with the moon? You only saw them when the two things aligned. One hypothesis had it that maybe the corona, for instance, was actually associated with the moon and not the sun. And here's an example of a coffee cup with steam coming off it and the sun's light coming from behind to illuminate that steam coming from the coffee cup. So maybe the corona was simply the atmosphere of the moon being illuminated by the sun passing behind it. So there was a big question. What is the corona? Who does it belong to? In 1860, Warren de la Rue was in charge of an expedition to Spain to see a total solar eclipse. And he had at his disposal the camera, the invention of the photographic plate and the camera. And he took along a telescope, he took along photographic plates, all the chemicals to create the emulsion, and then the chemicals to do the developing. He had a dark room. This was an evolved, elaborate event. You had a steamship that took him from England to Spain, then on a train, and then eventually horses till he got out into the path of totality. And what you see here are two of his photographs, one from the start of totality and the other from the end of totality. And what you can perhaps make out is that at the start of totality, the prominences all appear along that lower limb of the moon. But by the end of totality, all the prominences in the corona all appear at the upper limb of the moon. That right there is the conclusive evidence that rather than being associated with the moon, these are things associated with the sun. The moon is moving against the sun, against these phenomena. And I'd like to talk about Warren de la Rue here, because at the end of his report back to the British Astronomical Society about the results of his first ever photographs of a total solar eclipse and this discovery that the corona is due to the sun, he has this wonderful sense at the end in which he says, and if I ever get a chance to see another eclipse, I hope to do it with no equipment whatsoever and just take it in with my own eyes. So here's a warning to all of you photographers and wannabe photographers who want to photograph your first solar eclipse. Don't. Everyone will tell you, see your first, photograph your second. Do not waste those few precious moments of totality fiddling around with a camera. Just soak it in and enjoy the experience. All right. So what are some of those things that you experience? Well, as we said, there's the corona, this outer atmosphere of the sun. And in fact, that corona is startling in the fact that it is the hottest thing that any human being will ever see with their own eyes. It's at a temperature of over 1 million degrees. No star, the surface of no star is as hot as that, barring a thermonuclear explosion. There is nothing else that you will ever see with your own eyes that is that hot. All right, We've also got these red things. I've called them the prominences. These are eruptions of gas off the surface of the sun. Well, okay, what are those? All right, well, once again, we can go back to the 1800s. You had the start of spectroscopy, passing this light, the visible light that we see through a prism or a grating, and spreading it out to a rainbow and seeing what we can learn about the elements that make up the things that are giving off the light. So here we have a solar eclipse and the spectrum that was made from the prominences and the corona that were visible during totality. And for those folks who remember from their high school chemistry and physics classes, every single element on the periodic table has its own special fingerprint, thumbprint, if you will, of spectral lines, wavelengths that it and only it will give off. So in that fingerprint of light that we see from those prominences, there was the familiar red light and blue and purple from hydrogen. So immediately, astronomers realized that what you were seeing was hydrogen. The sun was made of hydrogen, and hydrogen gas was erupting off the surface. But there was this orange band of light that corresponded to no known element on the Earth. And so it was named after the god of the sun, Helios. We now know it to be helium. Helium was discovered on the sun in 1868. It was 25 more years, a quarter of a century later, before it was discovered on the Earth. That is just one of the many things that we learned from solar eclipses. But one more I'd like to talk about, because this one I find absolutely amazing. At the same time all this is going on, you also had this application of the physical motion, the interplay of gravitational forces between planets. And thanks to our understanding of gravity and very precise observations of the planets, in particular Uranus, astronomers discovered that Uranus was not moving exactly as Newton's laws would predict, if all the other planets interior to it and the sun were the only forces acting on it. This gave rise to the discovery of Neptune. Well, everyone was all absolutely delighted. Hurrah, physics has allowed us to discover a brand new planet for the first time. It's no longer chance or having to scan the heavens willy-nilly looking for things. We can now use the mathematical clockwork of the cosmos to discover unseen planets. Okay, that was in the outer outskirts of our solar system. But astronomers decide, let's apply this to the inner part of our solar system, in particular, the planet Mercury. Because just like with Uranus, astronomers have discovered that Mercury didn't seem to move exactly the way Newton's laws would predict. So the logical conclusion was there must be yet another planet interior to Mercury that was causing tugs and motions, changes in motions of Mercury. That putative planet was called Vulcan, and for a good chunk of the 1800s, at the time of every single total solar eclipse, when the light of the sun is blotted out and momentarily nearby stars and planets became visible in their reflected light, in the case of the planets, people sought to look for that planet Vulcan. And it was such a huge event with at every single eclipse, some astronomers saying they discovered a planet, other astronomers saying, no, I saw nothing, that it became quite the spectacle throughout the latter half of the 1800s. And so I have this quote here from Lewis Swift, who was the discoverer of so many comets that now bear his name. But I love this quote of his. I wish to again put on record that during totality of the solar eclipse of 1878 at Denver, Colorado, I saw two new stars, which I have reason to think were intramercurial planets. These are facts, and the world is challenged to disprove them. That's how cantankerous and controversial these planets eventually became. And as time went on, No planet was ever discovered. In fact, further refinements in Mercury's position led it to be, instead of one planet, it must be two planets. Instead of two planets, maybe three. Instead of three planets, maybe it's a belt of little planetesimals. Well, no planet was ever discovered. And maybe you all kind of know where this story is going, because it's the next big story in terms of solar eclipses, and that's Einstein's theory of relativity. In the early 1900s, Einstein came on the scene with both his special theory of relativity, which is how objects move at a constant rate, and how the passage of time and distances are affected by constant motion near the speed of light. But then the general theory of relativity took that to a more general stance on, well, what happens if objects are accelerating? And there were several conclusions that came out of this general theory of relativity. One is that mass warps the fabric of space. In fact, not just space, but space and time, space-time. So wherever you have mass, wherever you have gravity, in fact, gravity, what we experience as a force, what we all thought of as just a force between two objects with mass, was instead one object with mass warps the fabric of space around it, and other objects move along that warpage. In fact, light, which has no mass at all, is affected by gravity as it moves across this warp in the fabric of space and follows a curved path due to that warpage. One way to test this hypothesis, which was, again, hugely controversial, was through a total solar eclipse. And by the way, going back to Mercury, one of the other things that came out of general relativity was the explanation that Mercury's orbit was changed by it following along in this pucker, this warpage of space-time around the sun. So let's take a look at what's going on here. Here's the sun. It's sitting on what we can imagine to be a giant rubber sheet. That's space-time. It is warped, that fabric, due to its mass, so that as light from, say, a distant star travels along that sheet of rubber and it encounters that pucker, it curves around the sun. So when that light arrives here at the Earth, we see it as having come from a very different direction than it really did. So the star's position appears to have changed. It has an apparent position different from its actual one. But you may say, how on earth do we see a star that's very close to the sun? Because you cannot see stars in the daytime. But of course, there is one time when you can, and that's during a total solar eclipse. So there was the hypothesis. Here is a way that we can actually test it. So here's an experiment for our hypothesis. Einstein was working with a German astronomer to test this for a total solar eclipse in 1914 that was going to go across the Crimean Peninsula and Eastern Europe. Unfortunately, as those of you who may know history, in 1914, you had the outbreak of World War I. And so Einstein's German astronomer colleague was summarily arrested by the Russian authorities in Crimea, and all of his telescopic equipment confiscated for the rest of the war. So there was one eclipse that utterly failed to be useful for studying general relativity. And in fact, for the next 5 years, every attempt to measure that change in position of stars' positions around the eclipse failed. Bad weather, bad equipment, clouds. It was not until 1919, after World War I had ended, that Arthur Eddington attempted to measure this one more time. And he alone, where for the previous eclipses, there had been multinational attempts at this. At this point, in the end of World War I, everyone else was exhausted, they were broke. And looking back from the 2020s, let's not forget influenza. So there was also a international pandemic going on. So this was a terrible time to trying to measure this. But Eddington knew that he had the equipment, he could do it, he had the money, he had the backing. He sent two teams, one to South America to be in the path of totality there, another off the coast of Africa. The goal was to photograph the sun during totality and to actually measure the positions of stars around it. And then by keeping their equipment there for another couple of weeks, as the sun moved out of the field of view, and in fact, those star positions where the eclipse occurred would now be visible at night without the sun present, they could photograph the same star fields with the same telescopic equipment under the same conditions and be able to compare the two. And what we see here on the left is the newspaper headlines that came out of this. Eddington had been talking to the press for the year leading up to this. He had been submitting reports on his expeditions. The newspapers, the worldwide press was following along with bated breath. And so when he presented his findings, you got these headlines. And I just love these headlines. Lights all askew in the heavens. Men of science more or less agog over results of eclipse observations. I love that one. Einstein theory triumphs. Stars were not where they seemed or were calculated to be, but nobody need worry. And I particularly like this one. A book for 12 wise men. No more in all the world could comprehend it, said Einstein when his daring publishers accepted it. All right. So here's an actual photograph of the negative from this. And what you see is the eclipsed sun. And then between each set of hash marks is a tiny little dot, and that's the position of the stars. In comparing those positions to the known positions taken from 2 weeks later when the sun had moved away, these matched the predictions of general relativity. And scientists didn't stop there. They have been looking to test general relativity ever since. And here we have a Hubble Space Telescope image of what's called gravitational lensing, that ability of mass to warp the fabric of space around it and therefore warp the light that passes by it. What we see here is a relatively nearby yellow-orange galaxy, and behind it is a much more distant blue spiral galaxy. As that blue galaxy's light passed by the supermassive yellow galaxy, the warpage of space by that mass warped the light from the distant blue galaxy. It's called an Einstein ring now. Based upon the amount of curvature, we can now learn how much mass is there, and we can even learn about the distribution of mass. This is how we measure dark matter today. It's an amazing discovery that is still tested, it's still used, still refined, and still giving us benefits to understanding our universe around us. And so I want to come back to one last thing about eclipses. I've been talking a lot about the science behind them, but here's a photograph that I took from the deck of a four-masted sailing ship out in the middle of the Atlantic Ocean. I was one of the team leaders on a 3-week sailing trip across the Atlantic in order to catch totality off the coast of North Africa. And totality lasted for 43 seconds. And yet, think about it. If eclipses were just scientific phenomena, would people sail across the Atlantic for 3 weeks just to see 43 seconds of a scientific phenomenon? There's a wonderful quote from a psychologist. It says, science can be a powerful source of awe and wonder for many. It can provide a meaningful source of understanding oneself and the universe, and it can foster a sense of connection to others and our place in the world. And that's one of the things that science, be it the Milky Way or the Northern Lights or a total solar eclipse, can do. They can give us a sense of awe, which allows us to put ourselves in our place within this much grander, larger universe around us. And if you feel awe, you can feel connection, you feel humility, and you become much more connected to your world and your fellow human beings. And for those of you that have seen a total solar eclipse, think about that goofy smile on your face when you turn to the person next to you afterwards. It is a truly otherworldly experience. So let us not forget, the science of eclipses are amazing, but they are more than that. As my friend, Dr. Kate Rosso, a psychologist who studies this phenomenon, says, a total solar eclipse is above you, it's around you, and it's within you. And that's what makes this phenomenon, this unnatural, natural phenomenon, so special. So back in 2017, we had 12 million people moved to awe, living within the path of totality, not to mention all the other folks that traveled there to see it. In 2024, there are 31 million people living in the path of totality. Think about what that experience is going to be like, because whereas the 2017 eclipse went over many national parks and small towns, this time it's going over San Antonio, Dallas, Fort Worth, Toledo, Ohio, Cleveland, Indianapolis, Rochester, Buffalo. Major cities are in the path of this. Can you imagine what it is going to be like to see totality with 100,000 people around you all at once? So let's take a look at that path. It's going to start in Mazatlan in Mexico. It then hits the Texas border, San Antonio. Those lucky folks were in the path of both the annular eclipse back in October 14th, as well as the folks get to see totality next year. We then get Texas Hill Country. So whereas there were lots of big parks, famous parks like Great Smoky Mountains and Grand Tetons last time, this time we have some lovely little parks like LBJ National Historical Park. And then we have Dallas. You're at the Dallas Arboretum. What an amazing sight that might be. We then move from Texas up into Oklahoma, Hot Springs National Park, the first national park. Arkansas, Buffalo National River. It's going to be a lovely place. And then you get the Ozarks of Missouri. After that, we cross the Mississippi. And boy, those lucky folks in Carbondale, Illinois, they got to see the totality back in 2017. And here, 7 years later, they don't have to go anywhere else to see another one yet again. We then move on to Indiana, Evansville along the Indiana-Kentucky border, George Rogers Clark National Historical Park, Indiana. We then get to Ohio, Dayton Aviation Heritage. And I want to show this poster. And by the way, I guess I should mention, these are all my posters that I've designed for these parks. The last total solar eclipse to go over my part of the country, New York, was 99 years ago, back in 1925, January. The forecast for weather was so terrible on the ground that this new technology of airplanes and dirigibles was incorporated into eclipse chasing. Cameras were placed on all of these, and an entire squadron of biplanes was set into the air. And the news reports at the time said this was the largest squadron of planes since the Great War, all to fly off together to encounter totality. In fact, the weather was great, and people all over New York, including New York City, were able to see this. All right, those airplanes were built in Dayton at the Wright Company headquarters. So Ohio, Cuyahoga Valley National Park, Cleveland, all of Northeast Ohio are in the path of totality, including the national park there. So again, lovely, beautiful places, some very urban national parks in the path of this eclipse. Then you get to my state, New York, Niagara Falls, Erie Canal, the Finger Lakes. That's where I live. All right. From there, we pass on out through Montreal up in Canada, but Maine, Holton, Maine is the last town in the United States before totality passes off into Canada. French Canadian speaking Canada, and then to the Maritimes. All right, so this is a truly international eclipse. It's one of the reasons why we call this the Great North American Solar Eclipse. But let's just take one last look here at one state. And I'm going to use New York because that's where I live. If you take a close look, the totality comes ashore off of Lake Erie onto Buffalo. And they're going to get to see totality for over 3.5 minutes. So this eclipse is twice as long as the one in 2017. The moon's shadow is much, much bigger. So that's one part of the reason more people are going to see it, as well as the fact that it goes over these major cities. And in New York, Buffalo, Rochester, and Syracuse, 3 of the 4 largest cities in the state are in this path of totality. But I'm going to make the case that the most spectacular place to see this eclipse this time is going to be in Niagara Falls. Imagine you're standing there on the American side of those falls. The partial phase begins at 2:05 in the afternoon. Totality begins at 3:18. It's going to last for 3.5 minutes. And the location, I went out and measured this and worked with the rangers there. If you stand on the American side of those falls, totality is going to be straight over the falls, 45 degrees overhead. When I talked earlier at the very beginning about what a multi-sensory experience a total solar eclipse is, think about how much more multi-sensory it's going to be when you've got the crush and the roar of those falls as the temperature drops and dew forms on the hair on your arms. This truly is going to be a multi-sensory experience. High reward, also high risk. As we all know, the weather's best, at least forecast to be best, down in Mexico and Texas. But for my money, this would be the place that I would go if I had a chance to see a truly once-in-a-lifetime experience, a wonder of the world hosting a wonder of the universe. So with that, I want to thank everyone. Again, put in a plug for my book here, but also my website, tylernordgren.com, where most of those posters can be found. And I guess at this point, I will open up to questions. So thank you.